Hello and welcome back to the third part of Chapter 2, Motion in One Dimension. In this part, we're going to talk about the special case of constant acceleration. Acceleration has a very important role in physics, since as we're going to see in Newton's second law, that acceleration is directly proportional to the net force applied on the object. So whenever we apply a force on an object, we give it an acceleration, not velocity. And that's why it's important to discuss the case where we have constant acceleration. So if we have a constant acceleration and we plot the velocity function of time, the graph is going to be linear because the acceleration is constant and the acceleration is the slope of the tangent to the curve. So we're going to get a straight line. So the velocity changes linearly with time. Here we're taking the case where acceleration is positive. So we start at t equal to 0. So we're going to choose our initial time as t equal to 0. At that time, the initial velocity is vx0. And then it ends up at final time t, any final time t, with the velocity vx. The slope of this line is basically the acceleration, because here the tangent is the line itself. So we can say that the average acceleration is equal to the acceleration at any time because it's a constant. So if you take, for example, if you look at your grades and in each exam you took 15 over 20, so your average is going to be 15 over 20. So the average is the same as the instantaneous acceleration. And it's going to be equal to Vx, which is the final velocity, minus Vx initial, which is the initial velocity. We're calling it either Vx initial or Vx0. Over delta t. What we did is we chose that the initial time is 0. So we're starting our experiment at time equal to 0. So delta t, we can replace delta t by t, and then we can write the velocity vx at time t is equal to the acceleration times time plus the initial velocity vx initial. So this equation allows us to predict the velocity at any time t, just knowing t and the initial velocity and the acceleration. This is the first equation of motion with constant acceleration. Okay, what about the position? How can I find the position function of time? So if I know calculus, I could just do an integral. The opposite of a derivative is an integral. I know the velocity function of time. I could integrate and find the position function of time. But since here we have a special case of constant acceleration, I can use an arithmetic trick instead of using the calculus. So if I look at the average velocity, since here the velocity is changing linearly, I can say that the average between the initial time and the final time is just the sum of the initial velocity and the final velocity over 2. This is only true when we have linear change, so when the velocity is linear. So I also know that the average velocity, by definition, is the change in position, which is the displacement over delta t. And the change in position is just x final minus x initial. So I'm going to call, as I did with the velocity, I'm going to call the final position x and the initial position x0. And I'm going to choose the initial time as 0. So if I combine these two equations with the equation for the velocity, a function of time, vx, so I can find the position function of time in terms of three things: the initial position x0, the initial velocity vx0, and the acceleration ax. So all I need to know is the acceleration, and I know where the object is at any time t. The combination of these gives me that x is equal to x0 plus vx0t plus 1 over 2 ax t squared. So I got position to be quadratic in time, not linear in time, quadratic in time. Don't confuse that with cases where we have 0 acceleration. If in some cases, in many cases, we have object with moving with a constant velocity, it means that the acceleration is 0. In that case, the average velocity is the same as the instantaneous velocity, and I can use directly Vx average is equal to delta x over delta t. But in general, that's not true. So I have to know what is the constant and what are these values. So this equation only true when we have constant acceleration. Now, of course, zero acceleration is just a special case of this equation. There are actually three equations that we could look at. The first equation is the velocity function of time. Vx is equal to the initial velocity plus axt. The position function of time, x is equal to x0 plus vx0t plus half axt squared. And there is another equation that actually is not an independent equation. It's just I can derive it from the first two just by getting rid of time. It gives me the relation between the velocity and the displacement. So it tells me that Vx squared at any time is equal to Vx0 squared plus 2ax delta x. So it gives me a relation between the change in the square of the velocity to the displacement. These are called the kinematic equations for constant acceleration. Now here is some solving problem strategy for kinematics. It's from the book. So always visualize the situation. Try to draw a schematic of what's going on. Draw this object that we're talking about, that we're studying. Make sure before we use these equations that our acceleration is constant. Choose, of course, your axes in order to determine the signs. Determine the values that you know and assign, make sure that you have the right signs for the quantities, the acceleration, the velocity, and the position. Remember, when I choose the reference point and the direction, I determine what is the positive direction and what is the negative direction. And from the idea if the object is speeding up or slowing down, I should know if the sign of the velocity is the same as the acceleration or opposite to the acceleration. Of course, the rest is just you follow the problem and you try to find what's going on. Again, I'm gonna stop here for this lecture, and hopefully you enjoy it and it was clear enough.